AC voltage applied to a capacitor. In the purely capacitive circuit, as shown here, the capacitor is connected directly across the AC supply voltage. The capacitor is alternately charged and discharged as the current reverses each half cycle. Voltage across the AC source is V is equal to Vm sin omega t. Equation 1. Let Q be the charge on the capacitor at any time t. The instantaneous voltage V across the capacitor is V is equal to Q by C, where C is the capacity of the capacitor. Q is equal to CV. Kirchhoff's loop rule. From the Kirchhoff's loop rule, the voltage across the source and the capacitor are equal. Vm sin omega t is equal to Q by C. To find the current, we use the relation I is equal to dq upon dt. I is equal to dq by dt is equal to d by dt CVm sin omega t is equal to omega CVm cos omega t. I is equal to omega CVm sin omega t plus pi by 2. Equation 2. Omega CVm is the amplitude of the oscillating current, is equal to Im. Therefore, I is equal to Im sin omega t plus pi by 2. Equation 3. Rewriting omega CVm is equal to Im, we get Im is equal to Vm by 1 by omega c. Equation 4. Comparing this expression with I is equal to V by R, we find that 1 by omega c is analogous to resistance. It is called capacitive reactance and is denoted by Xc. Its unit is ohm. Xc is equal to 1 by 2 pi Fc. F is frequency in Hertz. Capacitive reactance. Figure shows change in capacitive reactance with frequency. Capacitors oppose changes in voltage by drawing or supplying current as they charge or discharge to the new voltage level. Capacitive reactance in a purely capacitive circuit is the opposition to current flow in AC circuits only. Xc is equal to 1 by omega c. Equation 5. Capacitive reactance is inversely proportional to frequency of the alternating current for any given value of capacitance. Xc is equal to 1 by 2 pi Fc. Substituting the value of 1 by omega c in equation 4, we get Im is equal to Vm by Xc. Equation 6. On comparing equation 1 and 3, we find that current phasor I is pi upon 2 ahead of voltage phasor V. Alternating current leads the voltage by phase angle pi by 2. Figure A shows the phasor diagram at an instant t1. Here, the current phasor I is pi by 2 ahead of the voltage phasor V as they rotate counterclockwise. Figure B shows the variation of voltage and current with time. We see that the current reaches its maximum value earlier than the voltage by 1/4 of a period. The instantaneous power supplied to the capacitor is Pc is equal to IV is equal to Im cos omega t into Vm sin omega t is equal to 1 by 2 Im Vm sin 2 omega t. Average power Pc is equal to 1 by 2 Im Vm average sin 2 omega t. Since average sin 2 omega t is equal to 0 over a complete cycle, therefore Pc is equal to 0.